Now we're given a function that has a bunch of stuff going on here, and we were asked about whether it was continuous at a few spots and then to give a tangent line. So in a case that, in order to answer some of these things, it's probably best for us to factor this out. This is x plus 5, x plus 2 on the top, and x minus 3, x plus 2 on the bottom. Okay, so at least now we have a little visual here. First question, is the function continuous at -5? So we see an x plus 5 here, and initially maybe that made you think no, but it's on the top. And so because it's on the top, it doesn't create a problem, doesn't make the denominator equal 0. So we would say yes, it's continuous at -5, and we would even say that f of -5 equals 0. There is no problem. How do I know it's a x? This is the x-intercept of f of x, or something like that. Okay, doesn't create a problem. Doesn't make the denominator equal to 0. All right. Now B says, is the function continuous at 3? Now x minus 3 is on the bottom. It's not canceling out. It's going to create a major problem for us. We would say for this one, no. F has a vertical asymptote, or if you said a non-removable discontinuity at x equal -3. We know that because it has the, at positive 3. We know that because it has the factor of x minus 3 that does not go away. Now C says, is the function continuous at -2? Now that we have a factor of x plus 2 in the function, but it's on top and bottom, it will cancel out. Does that mean that the discontinuity is gone? And the answer is no. We do have a discontinuity. So is f continuous? No. F has a hole, or a removable discontinuity, at x equal -2. If we could redefine that function at -2, make this a piecewise, say this is how it is for all x is not equal to -2, and then at -2 it equals whatever value could plug that hole, then we could make it continuous. That's not what it is, so we'd say no, it's not continuous there, it's just got a little hole in the graph, but that's enough to cause a problem for us. Now the last one says, can we write an equation of a tangent line at x equal 1? So the first things first, we're going to talk about a point and a slope. Anytime we talk about equation of a tangent, we're thinking point and slope. We know the x coordinate is 1. I need the y coordinate for this. So we're going to find f of 1. Okay, so according to our function, if I put 1 in, I'm going to get 1 squared plus 7 times 1 plus 10 over 1 squared minus 1 minus 6. All right, that's going to give me 18 over -6, which is -3. So for the point, when x is 1, y is -3. So at least I have that now. Okay. As far as the slope goes, I need the derivative. And for this, we're going to have to use a quotient rule. So I'm going to take the bottom, x squared minus x minus 6, times derivative of the top, which is 2x plus 7, minus top, x squared plus 7x plus 10, times derivative of the bottom, 2x minus 1, all over the bottom, x squared minus x minus 6 squared. Okay, so that's my derivative using quotient rule. Now I have to find the derivative at 1 to find the slope. All right, so yeah, that's a little bit of work, but we can do it. So if I go 1 squared minus 1 minus 6, that's a -6, times 2 times 1 plus 7, that's 9. Here I get 1 squared plus 7 times 1 plus 10, that's 18, times 2 minus 1, that's 1, over 1 squared minus 1 minus 6, that's -6 squared is 36. All right, so this is going to give me -54 minus 18 over 36, which is a -72 over 36, which equals a -2. That's my slope. Okay. So a lot of work to do there, but we end up with these here, and now I can go y minus y equals slope times x minus x. There's the equation. It's so simple, right? I mean, look at those numbers. Those are easy. Not easy to get, though. A lot of work involved in terms of using the quotient rule and being careful with our numbers. But the answer ended up looking quite easy.